All right, let's talk about something well, it's a huge shift in AI. We're moving beyond AI that just spots patterns in a spreadsheet. We're talking about an AI that can actually understand the fundamental shapes and structures of our universe.
I mean, really think about that for a second. The AI we have today, it's incredible. It can generate art, it can hold conversations, but it's kind of blind. It doesn't really get the 3D world we live in, the geometry of it all. So the big question is, what happens when we finally give it eyes? When it can finally see?
Okay, so let's get into the nitty-gritty. A huge limitation for a lot of today's most powerful AI is what people call the black box problem, right? The AI can spit out the correct answer, which is great, but if you ask it how it got that answer, crickets. It just doesn't have that deeper, intuitive feel for the structure of the problem it's solving. And this really breaks down that shift perfectly. On one side, you've got your standard statistical AI. It sees data as just a long, flat list of numbers. It's really good at finding correlations. When A happens, B tends to happen. But that's it. Now, on the other side, you've got geometric AI. It sees the same data, but as a rich 3D object. And because of that, it can understand the structure, the why. It can grasp causality. And that's the key to moving out of that black box into something we can actually understand.
So the question is, how do we actually do this? How do we give a machine geometric intuition? Well, it's not magic, even though it kind of feels like it. It's a brand new toolkit that mathematicians and computer scientists have been putting together. Let's dig into the core pieces.
First up, we've got something called a graph neural network, or GNN for short. And honestly, the best way to wrap your head around this is to think of it like a social network, but for things like atoms or even stars. In a molecule, for example, each atom is a node, and it's sending messages to all its neighbors about its properties, its position, stuff like that. And as these messages get passed back and forth, the whole network, the GNN, starts to build this incredibly detailed picture of the molecule's complete 3D shape and function. Now, this is where the real magic comes in. The secret ingredient is a principle called equivariance. It sounds complicated, but the idea is simple and powerful. It's basically a mathematical guarantee we build right into the AI. It means that if you show the AI a cat, and then you show it the same cat but upside down, it knows it's still a cat. Why? Because it understands the geometry of the cat hasn't changed, just its orientation. And that is absolutely crucial for understanding our world, where there's no fixed up or down.
So how does it do this? Through a process called message passing, and it's pretty much a three-step dance. First, a node gathers info from its neighbors. It aggregates. Then, it uses that info to update its own status. And finally, that new status gets propagated out. This whole process just repeats, and what starts as tiny bits of local information, like the bond between just two atoms, spreads across the entire graph. And that's how you get this incredible global understanding of the whole structure.
Okay, so this is all really cool in theory, right? But the most important part is, this isn't just a theory anymore. This new geometric way of seeing things is already out in the wild, being used to tackle some of the biggest scientific challenges we've got.
I mean, just look at this stuff. We're talking about cosmology, where it's helping scientists map out the vast, kind of sponge-like structure of the entire universe to figure out how it all began. Or think about medicine. This is a total game changer for discovering new drugs. The AI can predict exactly how a 3D drug molecule will fit into a protein, just like a key in a lock. It's even being used to build the next generation of encryption to protect our data from quantum computers. It's all about treating the universe for what it is, not a spreadsheet, but a massive collection of interconnected shapes.
But it gets even wilder. The applications go way beyond just analyzing data. We're heading into a future that honestly sounds like it's straight out of science fiction. Get this. What if you could take a purely abstract mathematical idea and 3D print it, turn it into a real, physical object you can actually hold?
This quote here really nails it. It's a radical concept. When you combine this geometric AI with something like 3D printing, you're not just making a model or a representation of a math concept. The object you create is the concept. It's the proof itself, made physical. A deep mathematical truth, literally sitting in the palm of your hand. And you can see here just how deep this connection goes. I mean, we all know about platonic solids and how they represent pure symmetry. But what about these more complex shapes? When you 3D print something like a star polyhedron, its weird self-intersecting shape is a direct physical embodiment of super abstract ideas from number theory. It's like the math is literally baked right into the material.
And this leads to an absolutely incredible implication.
If you can print one of these objects perfectly, with its shape dictated by pure math, it becomes a kind of universal, infallible ruler. Think about it. Any tiny flaw, any microscopic error in the print isn't just a printing mistake. It's a deviation from mathematical truth. That means we can use these objects to calibrate our most advanced tech, from the 3D printer that made it to a quantum computer, with a level of accuracy we've never had before. The object becomes the ultimate ground truth.
So, where is all this headed? What's the end game? Well, it's pointing us toward a completely new way of thinking about scientific and mathematical discovery itself.
You know, we're stepping into an era where the line between theoretical math and experimental science is getting really blurry. A mathematician of the future might not just work with a blackboard. They might come up with a hypothesis, use a geometric AI to explode the idea, and then they'll hit print and hold the result of their proof in their hands. The purely abstract suddenly becomes something you can test and experiment with.
And that final shift from abstract equations on a page to a real object, that could change everything. Not just our tech, but our fundamental relationship with the universe of mathematics. So I'll leave you with this thought. What happens when a proof is no longer just an equation, but an object you can actually hold? What new worlds will we discover when we can finally touch the answers?